Okay, so we're on section 2.6 now. We'll start off with some easy problems. And we're going to start with problem number 5. It says a point is moving along the graph of the given function such that dx dt is 2 centimeters per second. Find dy dt for the given values of x. So in this case, we actually have an explicit relationship. So, well, actually, we're taking with respect to time. So we have to use implicit differentiation on both of these variables, both y and x, because they're not t. So if we take the derivative with respect to time, y, that's equal to the derivative with respect to time of x squared plus the derivative with respect to time of 1. So what is dy dt? It's just dy dt, okay, because it's just y by itself. So, and then the second part, you take derivative of x squared and you get 2x, and then you multiply it by a dx dt. And the derivative of a constant is always 0, no matter what you're taking the derivative with respect to. So what we're looking for is find dy dt for the given values of x. So what do we know? We know that dx dt, the rate of change of x with respect to time, is 2 centimeters per second. And we need to know x. And x is, well, we have 3 values. We have -1, 0, and 1 for the 3 parts. So all we do is just plug them in there. So we could say dy dt at x equals -1 is, we just plug in -1. So we get 2 times -1 times dx dt, which is 2 centimeters per second. So 2 times 2 is 4 times -1 is -4, so we get -4 centimeters per second. So dy dt at x equals 0 is just 2 times 0 times 2 centimeters per second, which is 0 centimeters per second. And the final one, dy dt at x equals +1, we get 2 times 1 times 2 centimeters per second, and we get +4 centimeters per second. And I'm 99.99% sure that that answer is correct, but I'm just going to pull out the solution manual, because some of these later ones are a little harder, not super hard. Okay, just bear with me here for the first case. So I get -4, 0, and 4, which is correct. Okay, we're going to move on to problem 15. So these next couple are just area volume problems. So 15. The radius r of a circle is increasing at a rate of 3 centimeters per minute. Find the rates of change of the area when r equals 6 centimeters and r equals 24 centimeters. So the first thing we need to do is write an equation down which relates area to the radius. So area is equal to pi r squared. That's just probably somewhere in the book they give you that formula. Maybe in the back. Yeah, I think so. If you look at the back page of the book, you'll see some formulas for volumes and areas. So that is that. Now we're going to again take the derivative with respect to time. That's what we do in this section. So we take the derivative with respect to time of a is equal to pi times the derivative with respect to time times r squared. Notice I pulled the pi out because I could have done dt of pi r squared, but pi is a constant, so that comes outside. We don't have to worry about it. Well, we have to worry about it because it's there, but we don't have to take the derivative of it. So the derivative of just a variable with respect to another variable is just d whatever, d something, d whatever. In this case, d dt. Okay, pi, the derivative of r squared with respect to t is 2r. What's the derivative of r squared? It's 2r times dr dt. So that's what we're doing, and we're asking for find the changes of the area. Well, we already have it solved for d dt, so let's just clean this up. Sorry about that. Let me switch the microphone away. Anyway, so you get 2 pi r dr dt. So you can calculate the rate of change in the area by knowing the radius and dr dt. So let's look back at the problem. It says the rate of increase of the radius is, so dr dt, the rate of increase with respect to time, is equal to, it's increasing, so it's positive 3 centimeters per minute. So that's dr dt. R, we have two values. We have 6 centimeters and we have 24 centimeters. So this part, dr dt, is the same. What changes is r. So part A, dA dt, the rate of change of the area with respect to time, is 2 pi times the radius, 6 centimeters, times the value of dr dt, which is positive 3 centimeters per minute. And notice we have the units, and the units are, you multiply them together and simplify them if you can simplify them. So in this case, we'll have 2 times 6 times 3, which will be 36. So we'll say 36 pi, and the units are centimeters cubed, centimeters squared, sorry, centimeters times centimeters is centimeters squared, centimeters squared per minute. And that makes sense because we're looking for the rate of change in area. Area is centimeters squared times minutes. So that's problem number 15, 36 squared. Okay, so that's the first part, and that's correct. And so to do the second part, even though dr dt is the same, because the radius is higher, the increase in area is going to be bigger at that point. So we have 2 times, turn my calculator on, 2 times 24 times 3, which is 144 pi centimeters squared per minute. Okay, then we're on to problem number 20. So this is a volume problem, and it's the volume of a cube. So the volume of a cube is just the cube has equal length sides. So the areas of each side are the same, and the volume is just the length of the cube. Okay, all edges of the cube are expanding at a rate of 3 centimeters per second. So the length of each side is L, so the rate of change is, and it says increasing, so I think it said expanding, same thing, plus 3 centimeters per second. And we're asked to look at two values of L. So L is 1 centimeter, and L, second choice here, is 10 centimeters. So we take the original equation, take the derivative with respect to time for each part. Again, because we're taking the derivative with respect to time, and these are length measurements, you have to use implicit differentiation. So you get the rate of change of the volume with respect to time is 3L squared, which is the derivative we normally do as a power, times dL dt. So that's the expression. We need L and we need dL dt. Well, we have dL dt and we have L, so we just plug them in there. So for the first case, if L equals 1 centimeter, we get 3 times 1 centimeter squared times the rate of change, which is plus 3 centimeters per second. 3 times 1 times 3 is 9 centimeters cubed per second, because centimeters times centimeters squared times centimeters is centimeters cubed. So that's problem number 20. Let's check that out. So we get 9. Okay. And for the second case, if L equals 10, we get that dV dt is 3 times 10 centimeters squared times 3 centimeters per second. So 10 squared is 100 times 3 is 300 times 3 is 900. So we get 900 centimeters cubed per second. Change of the volume. Volume is centimeters cubed per unit time, which is seconds. So we get 900 is our answer. Okay, so let me check something here. Okay, just make sure it was recording. Okay, so we're going to the next problem, which is we're going back here to do 2 problems, 24, and then we'll do 27 and 34. 24, a conical tank with vertex down. So let's just draw that. So here's a triangle, and I'll just turn it upside down. So let's rotate that thing around. Okay, so there's your cone. Conical tank, vertex down, is 10 feet across at the top. And 11 feet deep. So from the top to the bottom is 12 feet. I don't know if I just said 11, but I meant 12. Okay, so that's that. Okay, so water is flowing into the tank. Let's use blue here. Okay, here's a hose. Water comes down, fills up the tank to some level. And let's call this Y. So from the bottom of the tank to the water level is Y. And they say that the rate of water is flowing into the tank at 10 cubic feet per minute. So cubic feet is volume, so dV dt, and it's increasing, so it's plus 10 feet cubed per minute. So that's dV dt. Find the rate of change of the depth of water when the water is 8 feet deep. So we're going to say Y is equal to 8 feet. And you look in the back of the book to find out what the volume of a cone, conical tank or cone is. So let's see. So right circular cone volume is pi r squared h over 3. So let's just write that down. Pi r squared h over 3. So in this case, h is the same as y. Now the question is, what is the radius? So they said the diameter is 10 feet. So we can say the diameter when it's full is 10 feet. And so the radius of when it's full is 5 feet. And what's going to happen is that when, say, y equals 0, r is equal to 0, because you're right down here at the bottom. And we can say that when y is equal to h, r is equal to the height, I'm saying the full height, r is equal to 5 feet. And it varies linearly because it's just like a cone. So what we could say is that y, or actually what we're going to say is r, the radius, is equal to, so it's going to be 5 feet. And what we do is we take y divided by h. h is 12. So let's see how that works out. When y equals 0, the radius is 0. When y equals equal to 12, 12 divided by 12 is 5. And in between it varies linearly, so that is correct. So that's the radius as a function of y. Because what you'll see is we actually have two things changing. We have the radius changing and the height changing. And we need to get this in terms of one variable. So what we can say is the volume is equal to pi times r, but r is 5y over 12. And we square that. And then the height of the water at any particular time is y. And so then we divide everything by 12. No, we don't. We divide it by 12, divide by 3. So we have pi r squared. R is 5y over 12. We square that. We multiply it by the height of the water and divide by 3. Okay, so that's our equation. So let's clean that up a little bit. So we have volume is equal to, let's see, 25. 5 squared is 25. 25 pi. We have y squared times y. So we get y cubed, all divided by 144. That's 12 squared times 3. Okay, so one more step here. 25 pi y cubed divided by, what's 3 times 144? 3 times 144 is 432. 432. Okay, so that relates to y, volume to y. And that's what we're trying to find. We're trying to find the rate, the change in the depth, which is y. So now we use implicit differentiation. So we take the derivative of the left-hand side, which is going to be dv dt. And that's equal to 25 pi over 432. And then the derivative of y cubed is 3y squared times dy dt. So we're given this in the problem. It's 10 cubic feet per minute. And we know y is 8, I think. Yeah, 8. So we can solve for dy dt because they're asking for the rate of change of the depth of the water. So let's do that. Dy dt is going to be equal to, okay, we have dv dt over here. Okay, so we multiply by 432. I don't know why I have 3y cubed squared right there. Oh, because I took the derivative. Okay, 3y squared. Okay, so we divide by, so we have 432 goes to the numerator. 3 times 25 is 75, 75 pi, and we also have y squared in the denominator. So those are all the constants. That's the rate of change of that's the volume. Okay, so now we can plug some numbers in. dy dt is 432 divided by 75 pi. dv dt was 10 cubic feet per minute. And then we multiply 1 over y squared. Y is 8 feet. And we square that. And this is problem number 24. So let me just get the answer. Make sure I'm going the right direction. See what they do. Okay, so they actually leave it in, they simplify this thing. So let's see what happens. So we've got 432, 64. Let's put everything over here. 432 divided by 64, 10 divided by 75 pi, and is that it? 10 times that, 75 times 64. So let's try 432 divided by 64. 6.75, so that doesn't quite work out. So let's try dividing 432 divided by 8. 54. Okay, so we get 54 over 8 times 10 over 75 with pi down there. And let's see what we have. So you've got 5 and 5 in there. Well, let's just multiply. Trying to figure out the easiest way of simplifying this. Well, you could divide both of these by 2. So you get 27 over 4. And you can divide both of those by 5. So you get 2 over 15. 75 divided by 5 is 15. Cancel. We've got the 1 over pi here. Okay, that becomes 2. That 2 cancels out with that. These both can be divided by 3. So you get 9 and you get 5. And so what do we have left? We have 9 in the numerator and 10 in the denominator. And so you get that. And that's the right answer, I'm pretty sure. It's problem number 24. What do they say for 24? 9 over 10 pi feet per minute. So that is correct. You see that we have feet cubed divided by feet squared, which is feet. Just want to talk about simplifying this thing. If we multiplied everything out, you get 4,320 divided by 64 times 75 over 4,800. Okay, now one way of simplifying this is you can kind of you can keep dividing by 2, but one thing here you can see that I've got zeros here, so I know that's 432 over 480. Okay, now what do we do now? Well, the easiest way is just keep dividing everything by 2 until you run out of opportunities to do that. So 432 divided by 2 would be 216. 480 divided by 2 would be 240. 216 divided by 2 would be 108. 240 divided by 2 would be 120. 108 divided by 2 is 54. 120 divided by 2 is 60. 54 divided by 2 is 27. 60 divided by 2 is 30. So you can't divide by 2 anymore, so what's the next number? 3. It's 27. You can divide by 3 and you get 9. 30 you can divide by 3 and you get 10. And so that would be another way of doing it. As far as simplifying the fraction, one advantage of this is I can do most of it in my head because I'm pretty good at dividing by 2. Going back here, I have no idea what number. And so by the time I probably guessed the number, I could just finish it this kind of simple mentally. Okay, this is problem 27, which is pretty complicated, and there's 3 parts to it. And to be honest, the first time I worked through it, I made a mistake. And so I'm re-recording this because I didn't want to have to confuse you guys. So here we go, number 27. We have a 25-foot long ladder. And it's going to be, let's see, the top ladder sliding down, so this end is sliding out. We're going to define the distance from the corner to the top of the ladder as y, and the distance from the corner to the bottom of the ladder as x. And so from the Pythagorean theorem, we know that x squared plus y squared equals 25 squared. So we need here's our relationship between x and y. And it also allows us to find x given y or y given x. So in our particular case, we're given three different values of x, 7, 15, and 24. Our relationship between x and y, the derivatives of x and y with respect to t, you just do implicit differentiation. So the derivative of x squared is 2x dx dt. The derivative of y squared with respect to t is 2y dy dt, and the derivative of 25 squared is 0. So you can solve for dy dt. It becomes negative x over y dx dt. Okay, so what you do is you take this to the other side, it becomes negative. You can get rid of the 2's because they're in each term, and you divide by y to get dy dt by itself. So that's our relationship. So if we have dx dt given, which it is in this case, that is 2 feet per second. And if we know x and y, then we can calculate dy dt. So the first part's actually pretty easy. So we have, we need to find the corresponding values of y because we have dx dt and we have the x values. So just using the Pythagorean theorem, we find out that y is square root of 25 squared minus x squared. And then you plug the three values of the x in, and they give you the three corresponding values of y. And then once you have this dx dt, x, and the corresponding y values, you can just plug them into this equation to find out how fast the ladder is moving down. And it is moving down because it's negative. So when x equals 7, y equals 24, this number stays unchanged for the different conditions. So you can see we get 14/24, which you can divide both of those by 2, and you get 7/12 minus 7/12. Okay, when you plug in x equals 15, you get negative 3/2. And when you plug x equals 24 in, y is 7, still 2 feet per second, and you get negative 48/7 feet per second. So those are the three parts for part A. For part B, we're talking not about our relationship. We still have our Pythagorean theorem relationship, but we also have our area, which is what we're looking at. Because it says, find the rate at which the area of the triangle changes. Rate means time. When the base of the ladder is 7 feet from the wall. So that's when x equals 7. So we've already know that when x equals 7, y equals 24, the hypotenuse is 25. So we have the area is 1/2 the base times the height. Here's the base, x, the height is y. So we have 1/2 x times y. Now, to find the ADT, we can take the derivative. There's two ways of doing it. I'll show you both ways. One way is to find x in terms of y, or y in terms of x, which in this case I'm doing solving for y. And then I'm plugging it in to make this all in terms of x. And then I can take the derivative. Or I'll do it the other way, which I haven't done yet, but I will do. This one gets a little hairy when you do the derivative. So if you plug y equals this from the Pythagorean theorem into here, you get that expression. So this is now just in terms of x. So you have a product. You have a constant times a variable term times another variable term. So these are the two parts of the product. So you take the derivative with respect to time of both sides. And one thing I do here, just to make the derivative a little easier to do, is I take this x, which is, so rather than doing a product, I'm going to make it into something where I just have to use the chain rule. So when you have x outside the square root, you move it into the square root, it becomes squared. So you get 25 squared times x squared minus x squared times x squared, which is x to the fourth. So that's no longer a product. It's a chain rule problem, where I have the square root of u, and u is this thing inside. So what do I get? Well, I have 1/2, which is my original constant here. I get 1/2 because this is the same. This numerator is equivalent to this 25 squared x squared minus 4 squared to the 1/2. It's the same as to the 1/2 power. So when I take the derivative, I get 1/2, which is the old exponent, and the new exponent is going to be is this whole thing to the minus 1/2 power. So that's what this is. So this is 1 over the square root of u, and this is u prime of x. So you take what's in here, and you take the derivative. So you got 625 times 2, which is the old exponent. 625 times 2 is that. And then you take derivative of this term, minus 4x cubed. So that's the derivative of this part. But you have to add dx dt because we're doing this implicitly, because this is t and this is x. Okay, so I think at that point we can just plug the numbers in. Let's see here. What do I do next? Okay, 1/2 times 1/2 is 1/4. Okay, so dx dt is 2 feet per second given from the problem statement. X is 7. So if I plug that in, I get 1/4, 1250 times 7 minus 4 times 7 cubed over the square root of 25 squared, which is 625, times 7 squared minus 7 to the fourth. And, okay, and the 2 comes from there. So what I do here is I take factor out of 7. So this is the same as 7 times the square root of 25 squared minus 7 squared. So there's the 7. And I cancel that out with the 7 that's here. So what that leaves, if I get rid of that, I get 1250. And if I have 4 times 7 squared, 4 times 49 is 196. So that's kind of what that is. It's a little cryptic. And then I have 25 minus 7 squared. Okay, so factor out 7. And really I had this times 7 and this times 7. And I cancel those out. So 7 cubed becomes 7 squared. 7 squared times 4 is 196. And then you just have 1250 left over. Okay, subtract those two, you get 1054. This 2 cancels out a 2 in there, so 2/4 is the same as 1/2. Again, that's 1054. And the denominator, 25 squared minus 7 squared, take the square root is 24. We've done that. We just did that a minute ago. And so you get 1054 over 48, which is 527 over 24. So that's the answer for part B. That's DADT. Okay, that's number one way to do it. The second way to do it. The first way to do it is you go back to here. A is equal to 1/2 x times y, base times height. So you take the derivative with respect to time, and you get 1/2, and you've got a product. So you've got the first term times the product times the derivative of the second, plus the second term times the derivative of the first. Okay, for our particular case, x equals 7 feet, y equals 24 feet. This squared plus that squared equals 25 squared. Dx dt is equal to 2 feet per second. And dy dt is, well, we go back to part A. When x equals 7, dy dt was equal to -7/12. Okay, so now we should plug it in. So you can see this one's actually it's a lot easier to do this way than the way I did it, but it's still valid. Okay, so you get dA dt is 1/2 x, which is 7 feet, times dy dt, which is negative 7/12 feet per second. And then you add y, which is 24, and you multiply by dx dt, which is 2 feet per second. So this was feet times feet per second. You get feet squared per second. Okay, 1/2 times negative 49/12 plus 2 times 24 is 48. 2 times 24 is 48. So let's put it with a common denominator of 12. So you get 1/2 times negative 49/12 plus, okay, so to get the next one, you multiply 48 times 12. 48 times 12 is 576. 576/12. So we get 576 minus 49, 527. Plus, so it's plus 527/12. And you see 2 times 12 is 24, so you get 527/24. I think that's what we got down here. 527/24. So the ADT is that way. So that's part B. And then part C is, let me just put a little screen up here so you don't get too ahead of me. So we know that from the right triangle geometry that the tangent of the angle between the lower things, so let's go back to the drawing so I don't have to do the drawing. So this would be theta, right? Angle between the ladder and the wall. Angle between the ladder and the wall. So that's the angle between the. So this is theta. So when x equals 7, the tangent would be 7 divided by 24. Okay, where am I here? Ah, there we go. So it's x over y, opposite over adjacent. So you take the derivative of each side with respect to time. So we take the derivative with respect to time of the tangent of theta. Well, the derivative of the tangent is secant squared. So it's secant squared of theta, but then we have to add the d theta dt on the end. Here we have a quotient. So use the quotient rule. So it'll be the derivative of this with respect to time. So it'll be dx dt times g of x, which is the denominator. So let me just write it out. I got it right here. So the derivative of the first term is just dx dt times the second times the denominator, g of x, minus f of x times g prime of x, all divided by g of x squared, or whatever, the g, the denominator. And I'm going to go ahead and break this into two terms. So y over y squared is 1 over y, and negative x over y squared is negative x over y squared. So we bring this term just straight down, and we rewrite this. So we have 1 over y times dx dt minus x over y squared dy dt. Okay, what we're trying to find is d theta dt. So we're going to divide by the secant squared of theta to solve for d theta dt. Well, 1 over the sine, whatever the secant is the cosine. So when I divide by secant squared, I'll get 1 over secant squared, which is the same as the cosine squared. So we have the cosine squared of theta times some stuff right here on the right-hand side. So if I could find all these numbers, then I'm in good shape. Well, y is 24, x is 7. We did that previously. Dx dt is given in the problem is 2. dy dt from part A we calculated when x was equal to 7 and dx dt was 2, we calculated dy dt is negative 7/12. So we got everything except the cosine of theta. We don't actually have to calculate theta. We know that the cosine is the adjacent, which is 24, divided by the hypotenuse, which is 25. This squared plus that squared equals 25 squared. So the cosine of theta is 24, the wall height, the height along the wall divided by the hypotenuse, which is the length of the ladder. So we can plug all those in. 24 25th squared times the quantity 1/24th, which is 1 over y. dx dt is 2 minus x 7, y is 24, so we square it. And then we multiply by dy dt, which is negative 7/12 from the first part. So now we just need to simplify it. And it's actually comes out to be a surprisingly simple fraction, given how complicated it looks initially. So what I do here is I get a common denominator. I have a 12 and I have a 24 squared. So I multiply it. This already has 24 squared and 12 in the denominator. So I multiply this by 24 in the numerator and the denominator. So 2 times 24 is 48. And 24 times 24 is 24 squared. And then you multiply by 12 in both the numerator and the denominator. So that's where that 12 comes from. And now I have the common denominator here of 24 squared times 12. 48 times 12 is 600, well, 48 times 12 plus 49, because you have a negative times a negative, plus 49 is 625. So we have 625 in the numerator, 24 squared times 12. So these cancel out. These cancel out. 625 is 25 squared. We get 625, which is 48 times 12 plus 49. And that leaves 1/12. So the answer is d theta dt is 1/12 radian per second is the rate of change in the angle of the ladder. Okay, so now we're going to get to some more complicated ones for the rest of the time. Some basic principle applies. We come up with some geometric relationship, and then we take the derivative with respect to time. So this is with figure 28, and I'm just going to kind of draw a simplified version of what it is. You have a wall like this. You have the ground like this. You have a ladder, which I'm going to make red, actually make it blue. And there it is. That's the ladder. And we're going to say this is y going up this way. We'll say y equals 0 there. So that's y. And this is x. Okay, so let's read it. The construction worker pulls a 5-meter plank. So this side is 5 meters. It's a plank, so it's not going to change in length. That's fixed thing. So that's the length of that side. Up the side, a building by a rope. So we're going to pull on this end, and this end will come up, and this end will slide to the right. Okay. Assume the opposite end of the plank follows a path perpendicular to the wall. So this side, so what it's saying is when you pull up on this, it's going to stay on the edge of the wall, and this other end is going to stay on the ground. And the worker pulls the rope at a rate of 0.15 meters per second. So what we can say is that dy dt equals positive 0.15 meters per second. Okay, it's positive because positive y is going this way, and so we're increasing y. How fast is the end of the plank sliding along the ground? So this is our x. So what we have is basically, we'll actually call this distance y, not just the axis, but the distance from the corner, and we'll call this distance x here to that end. So that's x and y. So a lot of these cases, these geometry cases, are the Pythagorean theorem. So the Pythagorean theorem says if you have a right triangle, which we do, then the one side squared, length of one side squared plus length of the other side squared is equal to a constant, in this case 5, because that side, the hypotenuse is always going to be 5 because it's a plank. It's not going to get shorter or longer. So that's the equation that governs things, x and y. But what we're looking at is the derivative with respect to time. So we take the derivative of x squared with respect to time, and we add the derivative of y squared with respect to time, and that equals the derivative of 25 with respect to time. Well, the derivative of a constant, it was 0, so that goes to 0. Here, because we're taking the derivative with respect to time, what we get when we take the derivative is 2x, which was not what we normally think, but we also get dx dt. And likewise, y is not t, so we take the normal derivative and we multiply by the normal derivative of y squared, but we add this dy dt on the end of it. So that's the relationship. We just have to solve for what they're asking for us, and they're saying how fast is the end of the plank sliding along the ground? Well, the ground is x, so what we're going to do is solve for dx dt. We can divide everything by 2 to get rid of those. This divided by 2 is 1, this divided by 2 is 1, 0 divided by 2 is 0. So, okay, now let's move this term to the right-hand side. So we get x times dx dt is equal to negative y times dy dt. And then to solve for dx dt, which is what we're trying to figure out, you just divide both sides by x. So we get negative y over x dy dt. And to solve these problems, you're going to have to know 3 out of the 4 things. We know we have 2 rates and 2 variables. So it says, how fast is the end of the plank sliding along the building when it is 2.5 meters from the wall of the building? So what that means is, in this case, x is equal to 2.5 meters. So we have dy dt, we have x, so how the heck we need y? Well, we just use the Pythagorean theorem. So we know that we can solve the original Pythagorean theorem, not the one before we take the derivatives. That one there, and you'd have x squared plus y squared is 5, therefore y squared is 5 squared minus x squared, or y is equal to the square root of 25 minus x squared. And it shows the positive root. Mathematically, we'd say, oh, it's plus or minus, but in reality, it is positive because it can't have negative lengths, just like you can't have negative time. Okay, so 2. So square root of 25 minus 2.5 squared. So we'll pick y when x equals 20 or 2.5, and I get 4.33. 4.33, and the units are meters. So meters, okay. So now we do have everything. So all we have to do is just plug it into the equation. So the rate of change, sorry, I did that wrong. I'm supposed to be solving for dy dt. How fast is the end of the plank sliding along the ground? Oh, no, that's right. Dx dt is negative y dy dt over x. There we go. Okay. So dx dt, let me change back to the blue. Okay, so dx dt is negative y. Y was 4.33 meters divided by 2.5 meters times dy dt, which was positive 0.15 meters per second. So dx dt, 4.33 divided by 2.5 times 0.15, and you get negative 0.26. And the units are meters per second, because these meters cancel out with each other and just become one, and we just have the units. And you'd expect dx dt and dy dt to be the same units, because they're both rate of change of length. And it's negative because x is getting shorter. The board is getting closer to the side of the building. So I'm just looking at the answer here. Negative 0.26 meters per second is the answer. Okay, this is our last problem in this section. And this is a baseball problem. Okay, so it says for the diamond, baseball diamond exercise 33, suppose the player is running from first to second at the speed of 28 feet per second. Find the rate at which the distance from home plate is changing when the player is 30 feet from second base. So here is second base, here's first base, here's home. So we're going to put the player in here somewhere. So we have that. That distance doesn't change. That distance is 90 feet. Then we have here and like that. And this angle is 90 degrees. And so this distance is 90 feet. So we're going to be able to use Pythagorean theorem. And let's see, what are we asking for? And I suppose the player is running from first to second at a rate of 28 feet per second. So let's call this x. So we know that dx dt equals 28 feet per second. Find the rate at which the distance from home plate is changing. So this is our distance. We'll call that s. So we've got two legs of a triangle. One, this is changing. This is changing. We know this is. We know that this guy's running at the same speed, and then we want to know when it. Find the rate at which the distance when the player is 30 feet from second base. So this is 30 feet. So if that's 30 feet and it's a diamond, then x is equal to 60 feet. So what we can say is that x squared plus 90 squared is equal to s squared, because this is the right angle is right here, not here. So this part, the hypotenuse is changing in this case compared to the ladder problem where the hypotenuse is constant. So you can see we're going to need x, which we know, 60 feet. We're going to need dx dt, which we know, 28 feet per second. And s, well, we know s, because we know x. So s squared is equal to 60 squared plus 90 squared. So 60 squared plus 90 squared, take the square root of that. So this squared was 11700 feet squared, so s, take the square root, is 108 feet. So those are all the known things we know. We also can then take the derivative of this with respect to time, so we'll get 2x dx dt plus 0 is equal to 2s ds dt. And what we're trying to find is ds dt. So we just have to solve for ds dt. And so that's equal to negative, 2's cancel out. So we'll get negative x over s dx dt. And I was just thinking, oh, we don't have a negative in this case. That was what was bothering me, okay, because we just divide by s, so it's going to be positive, because when dx dt is positive, ds dt should be positive as well. That's what was throwing me off. So we just get ds dt is equal to x, which is 60 feet divided by 108 feet times dx dt, which is 28 feet per second. (28) times 60 divided by 108. 15.6 feet per second. And that was problem number 34, so we'll just check the answer is 15.6 feet per second. Okie dokie.